Chapter 3, the kinetic theory of gases. Here's an overview. We want to do four things. We want to derive the ideal gas law. And the reason why we want to do that is because it introduces many important concepts. 2, we want to expand the ideal gas from monatomic gases to diatomic and polyatomic. Now that we have an ideal gas, how does it look like when we apply it to a real gas? Real gas particles actually collide. And then 4, we want to talk about the Maxwell-Boltzmann speed distribution, which leads to evaporation and boiling. So here we go. Lecture 3.1. The ideal gas law derivation shows how microscopic collisions with a wall cause macroscopic pressure. There are 3 main pieces. 1, we have to calculate the average force applied by n gas particles on a wall of the container. 2, which is the trickiest ones, which is the tricky piece, the number, which I call n collisions. So how many gas particles are actually colliding with the wall has to be calculated. The number of n collisions of colliding gas particles with a wall. And then we finally start talking about the RMS speeds of a randomly moving gas particles. And then when we put all 3 of these together, it's going to be quite easy to then finally calculate the pressure. Okay, so let's do that. So our first step here, we want the average force of n gas particles colliding with the walls of the container. So here we go. A gas particle collides elastically. So what that means here is that they change direction, but the speed before and after are exactly the same. The velocity changes. So as a gas particle collides elastically with a wall, the speed stays fixed, so if I'm looking in one direction, that tells me here that the speed in the x direction must also be the speed coming after the collision. So the speed stays fixed, but velocity changes. So let's look at this thing here. So here's my wall. Okay. So if I look at my wall, I'm going to have a gas particle that comes in. So again, this is the wall of the container. And what I'm going to do here is that I'm going to make this my positive, my negative and positive direction. So this here is the direction. So we know what it is. So now I have a gas particle that's coming in, and it's going to be moving in this direction. And look what I'm going to do. This is moving, that velocity is moving in the negative direction. This guy, after the collision, now moves in the positive x direction. So then I have a change in momentum. And what do I mean by a change in momentum? So if I look at the momentum in the x direction, I'm then going to get that minus, and remember, there's that second minus sign right there. And that's going to be this, oops, not that. It's going to be this guy. And so because the speeds are the same, I'm going to get 2mvx, and that's going to be the change in momentum in the x direction. So now I have this change in direction. Now, I think it's worth talking about this because I think, again, there's a lot of good physics in deriving this. And I'll say here is that there is something quite interesting about delta P. Okay. Now note that this is a vector quantity. What happens here is that all observers measure the same delta px. So what do I mean by that? I could pick 3 frames just off the, off the top of my head, but let's look at this thing here. So you know what I'm going to do here is I'm actually going to copy this guy right here. Okay, so I'm going to put this guy right here. Okay, because this is what's happening right here. And then I'm going to place this guy again, and I'll only do 2 frames, but I'll mention 3 frames. So I could have an observer right here. And I'm going to say that this is observer number 1. And in this frame, this is called the lab frame. And in the lab frame, which is what we typically talk about, that momentum is measured to be 2mvx. That's what we just did. Now, if I jump into a second frame, and I'm in the frame of one of the particles, and I'm going to call this guy 2. So I'm actually in the frame of one of the particles. If you measure that change in momentum, you also get 2mvx. I can also do the center of mass frame, which I won't, but you also get the same change in momentum. So why who cares, right? It is this fact that is that all observers see the same, delta px, it is this fact that this is independent of reference frame. This is the cause of why, check this out, temperature is frame independent. In classical physics. That's a pretty big deal. Because then all observers always measure the same temperature. Now note, that's not true when you get to relativity. There is a frame dependence that you have to account for. But in classical physics, all observers always measure the same temperature. Now, getting back to what we're started here, the impulse momentum theorem states the impulse applied by the wall changes momentum. So if I look at this, this is how we define it. The change in momentum is then going to be the force applied or the impulse of the wall, or I can also write this using the mean value theorem for integrals. So there's two ways to write this. So this is the mean value theorem for integrals. So what does this really mean? Well, let's say, so if I look at the impulse with the integral, it really says this. So if I look at this guy, I'm going to have an impulse that's typically, we like to say that it's symmetric. And so if I now look at this area of this guy, right, that integral tells me about the area. This guy is the area of that impulse integral, where this term right here, that's T1, that's T2, and of course, that's the force right there. On the other hand, we have something else. The mean value theorem says, as long as the areas are the same, I can't tell the difference. So in other words, if I pick a point that has the exact same contact time, I should say, then as long as this area and these two areas are the same, And we got to be careful with what we mean here. This average here is a timed average. Okay, so it's a time average. What we're finding here is that these two guys, if these areas are the same, then I could make that replacement. And so that's what we want to do. We want to use the average force. So now I have the average force times the time interval is going to look like this here. Now, we got to be a little bit careful with this guy right here. This right here is not the contact time. This is the time it takes to collide with a wall. And you'll see what I mean by this. So now, here I go. I have calculated the average force, and it's going to be 2m Vx divided by delta t. Okay? And so what you're seeing here is that this is the average force by a single gas particle. So now what we need to do here is that we just have to extend it. So now, to extend this to n gas particles, one multiplies F average by n. In other words, I now have the average force, and this is for n particles, and this is going to be n times 2mvx over delta t. So now we've calculated our first piece of the puzzle. Now let's go to step 2. We need to calculate the number of collisions, which I'm going to label n with a wall, right? We want to calculate the number of collisions. And what I'm saying here is that, of course, not all the particles are colliding with the wall at the same time. So here we go. So now, not all gas particles collide with the walls at the same time, which we need to account for. So in this case, what we're really doing here is that we're going from n to n collision. Okay? So what I'm really looking at is that I'm looking at this. So now, if I look at the average force, I'm going to rearrange this, and this is what's going to happen. I'm going to have the number of collisions per unit time times 2mvx. That's what we're after right there. Okay, that's what we're after. So now let's go look at that. So we have to calculate that. So what I'm seeing here is that n collisions per unit time represents how many collisions occur per unit time. And this is, without any doubt, the most challenging part of the calculation. Okay? It's by far the hardest part of the calculation. So here we go. So what I want to do here is that I want you to start to visualize here. So let's see if I can draw a picture. So I want you to visualize the situation. So because only a fraction collide with the walls, we ask how many collide within some time delta t. And it turns out that because particles are moving, that means that the gas particles span some space. So how am I going to draw this here? So I'm going to draw a cube, not a cube, a rectangle. So let's look at this. So how am I going to draw this? I'm going to go, and then let's say that I'm going to go up to here. And what I'm going to do here is that let's set up my, you could imagine that I'm coming down to here. And so what you're seeing here is that here's my box. So now I'm going to start to separate this guy up. So I'm going to say that I'm going to look at this yellow part. Okay. So should have planned this a little bit better in my picture. So I'm going to have a yellow box. And what you're seeing here is that the wall that I'm going to focus on is this end right here. And I'm going to say, here's my area of this thing, and this is where the gas will collide with area A. So now what you're seeing here is that if I look at a gas particles within here, I'm going to label these guys like right here in green. And what I'm seeing here is that these gas particles, the green ones, are all moving to the right, let's say. And then I have gas particles that are moving to the right, or left, excuse me. So what am I trying to do here? So the first thing that I'm trying to do is that I'm going to say that the yellow region represents the number of particles colliding within a time delta t with the right wall. So this is really important right here. Within a time delta t. So that means these particles span a space. Now note that this is an important detail. And the reason why this is an important detail is that this pops up again, this idea of particles spanning a space. And so what this tells me here is that this is going to, that's the space delta x. And so this tells me here is that I'm going to have some speed over that time. And so it really represents a cube of how these particles are moving to the right and collide within a time delta t. Now, random motion implies only half are moving to the right. That implies I have to add a 1/2 factor here. Okay, so now let's put this all together. So now, putting this all together, we now have this here. We now know that the number of collisions must be this. Well, I have to have a 1/2 factor because half of them are moving to the right. Now, in that yellow region, we assume that we have a constant number density. So I have a number density that's constant. And so that's got to be the value n divided by v. And that just says that if I was to look at this, that just says that the number of particles are uniformly distributed throughout the volume. That's all it says. So I haven't really done anything, haven't said anything yet. But note, this has units of numbers divided by volume. So now what I have here is that I have to account for the volume. You know what? I think I should do this. I think I want to call this yellow. Okay, so I'm going to go. I don't know how big to make this, but let's say it's to write everything in. So this is the spanned volume. That's the yellow box here. So then this is the volume spanned. Uh-oh. Should have made it a little bit bigger. By moving particles. Right? So this right here is that yellow volume. So what I'm doing here by the span volume is that I'm only picking a percentage of those particles. So now, if I put this all together, it's going to look like this. So I'm going to get 1/2 times the volume density, the number density, which is constant. And then the volume is then going to be the area times that distance spanned. So then what you're seeing here is that I could then write this as 1/2 n divided by v. And this now is A times Vx delta t. So now what I'm going to do here is that I'm now going to solve. So if I now solve for n collisions per unit time, then I isolate the term where I get 2 times the volume times the number density, the number density, of course, and then this will be AVX. So now what I'm seeing here is that I'm seeing this guy here. And so now this is the rate. I just said the right wall, but this is the rate of collisions for all the walls of the container. It's not just for the right. Now there's some good observations here that's worth looking at. The first observation that I would say the first thing is that there is no mention of the type of gas particle. That implies it's independent of gas. Okay, that's important right there. Okay, so then 2, never in this derivation does 1 discuss collisions between gas particles. In other words, ideal gases do not collide. We never accounted for that with each other, except with walls of the container. And if they're point particles and they have no volume, then of course they can't collide. So now, here we go. This is really freaking awesome right here. So now, adding in collision per unit time to the average force equation yields that the average force, which we had already written as n collision per unit time, times 2 mvx. So if I put everything together, look what happens here. I get n over v times the area, and look what pops up, mvx squared. Look at this. This term right here, look at this. You could see here is that now kinetic energy enters the picture. For the first time, we're seeing how kinetic energy pops up. Now, we're in our final step here. We got to deal with that velocity. So here is step 3. Calculating 3-dimensional speeds. Okay. And now we're headed towards the RMS speed. At this point, the model claims all particles move with the same speed, Vx. Obviously, that can't be true, right? Not true. So we need to relax this assumption. By using averages. So in other words, what we want to do here is we want to replace Vx squared with V average x squared, where the bar means average. This presents a problem. Since half the gases move right and left simultaneously. So you could imagine that if I have a box, let's say that this is my box right here. Okay, here's my box. I'm going to have, let's say on average, I'm going to have particles that are moving to the left. On average, I'm going to have particles moving to the right. So then that means here is that the average velocity is then going to be v to the right plus v to the left, and they have to be vectors. On average, that has to be identical to 0. But, and we physically, this must be true. Why? Suppose one has a box filled with a gas. How about a box of air? Let's say that you have an empty box on the table and it's filled with air. If the average was not 0, then the box would suddenly and mysteriously accelerate, right? For no reason. That would violate Newton's second law of cause and effect. We know that this does not happen. Therefore, the average speed must be 0. Okay, so what we need to do here is that we need to deal with a different quantity on averaging. And this is what leads to the RMS speed that we've been talking about. So what does RMS speed here? So the first thing you got to do is that the S stands for you square velocities. So therefore, what this does here is it eliminates the sign issue, right? Because when we look at this box, one of these is negative. Let's say that going to the left is negative. There's a sign issue. By squaring it, that doesn't happen. And then what we do here is that we then take the mean. And the mean, of course, means you now average the velocity squares. And then finally, to get the proper units, you take the square root. Get proper units. So here it is. VRMS is then equal to what? The squares of the velocities. I then average them or take the mean, and then I take the square root to make sure that I get proper units of meters per second. This is the RMS speed. So what does this mean here? So the mathematical difference between V average versus VRMS looks something like this. Now imagine that we have 5 speeds. So we have five speeds. Let's calculate these things. So we could see we have 500, 600, 7, 8, 900. So these are five speeds. Right away, you could see that the middle is 700 meters per second. But let's calculate it nonetheless. So if I look at V average, I have to add all of these guys up. So I'm going to go 500 plus 600, and I'm going to go all the way to 900. And because there's 5 of them, we add these up, we get 700 meters per second for the average speed. Now let's compare that to VRMS. So if I look at VRMS, what I do differently now is that I take the squares of all of the speeds, Then I average them, and then I take the square root. And what you see here is that I get a number of 714 meters per second. So you could see here that there is a slight difference between the two. Okay, so one sees VRMS is slightly larger than V average, right? Which implies VRMS, because of the square, slightly favors higher speeds. Right? So RMS, it's close, it's not the same, but at least we don't have that sign. So it's a type of average. Okay, so now let's extend this the velocities from one-dimensional to three-dimensional. By the way, it was Maxwell, from Maxwell's equations in electricity and magnetism. He was the first one to actually do this. So Maxwell claimed a randomly moving gas has RMS speeds along the X, Y, and Z directions. And that's not a surprise. But this is what he says. And on average, they should be the same value. So this is what he means here. So remember, so we go Vx RMS should be the same as Vy RMS for a random gas, right? And then Vz RMS. Now, I don't want to write VRMS. So look what I'm going to do now. So if I'm going to say RMS, we know this is a type of average. So from now on, I'm just going to use the bar to talk about RMS. Just to be clear. So then, here we go. So now we deal with velocity squared. So then VRMS should then equal what? It should be Vx bar squared, Vy bar squared, Vz bar squared. Right? And this is for a 3D gas. But guess what? These guys on average should be all the same. So it's now 3Vx bar squared. So this guy is for this is the 1D value. So then Maxwell says that I have Vx bar squared is equal to 1/3 of V RMS squared. This is Maxwell's conclusion. Okay? And you can see here is that the 3 comes from Vx, Vy, Vz. Of course, they're all RMS values. The 3 enters. That's important right there. Because when you think about the heat capacity, where does that 3 come from? It comes from this guy right here. So now what we want to do here is that now let's put this into the average force equation. So here we go. We said that the average force applied by N gases is going to be N over V. And then we said that we had mvx squared average times the area. So now this is for a 1D gas, but now we're going to a 3D gas. And the 3D gas gives you that factor of 3. So now we find that F average is now going to be N over 3V mv RMS squared times area. So now we can do the last step. So this is not really a calculation. It is a calculation, but it's really a definition more than anything. So now we derive the ideal gas law now. So from the definition of pressure, here's what we get. We say that pressure is equal to the average force divided by the area. So then check this out. I have area here. Then I'm going to get N over 3V mv RMS squared times area. And you can see here that these areas cancel out. So rearranging this, here's what we get. I'm going to take the volume to the other side, so I'm going to get PV, and this is then going to be 2/3 N times, look at that, so I put in a 2. 2 divided by 2 gives me 1. I'm going to get 1/2 mv RMS squared. In other words, I'm going to rewrite this as 2/3 N times K RMS, which is then going to be pressure times volume. Doesn't look familiar to, but this here is the microscopic form of the ideal gas law. That is the microscopic form of the ideal gas law. And there's some pretty interesting things here. Okay, so let's look at this here. So now let's interpret what we have here. Okay, so we want to interpret. So the first thing that I note is this. Pressure is caused by numerous collisions by point particles with the walls of a container. Note, this is the connection between micro and macro scales. This literally makes the connection. 2, there are 2 kinetic energy terms in the microscopic ideal gas law. There's 2. One, there's the average, right? RMS average, the average randomized translational, which is what we call RMS, kinetic energy of a single, gas particle. Right? Because when I look at this thing, here's what we mean. We say that if I have a single gas particle, this KRMS is also the K translational of a single gas particle, but I'm not going to call it translational. Most of the time I call it KRMS, and then this guy has to be 1/2 mv RMS squared of a single gas particle. Okay? That's one of the kinetic energies. There's a second. The second is the total kinetic energy is what we call the internal energy, what we call K micro. And that is the total number of particles with K RMS. We've been saying that this was the internal energy, but we've never really said very much about it other than this. So let me talk about the third thing here. Let's see here. Yeah, let's talk about 3. 3 here. So now we can compare the micro versus macro forms of the ideal gas law. So here's what we see here. So we see here is that the micro is what? It's 2/3 NKRMS. This right here is the micro, which we just derived. Now, if I look at the macroscopic ones, there's 2 forms. It could be written as nRT, or it could be written in the NKBT, where KB is the Boltzmann constant. And what you're seeing here is that this here is per mole, and this is the macroscopic, and then this guy is per particle. And if it's per particle here, this has to be the microscopic version as well. So we can derive the temperature using these relationships. So we see here is that PV is going to equal to N kBT, but then this is also N times 2/3 KRMS, which then tells me here that KRMS is equal to 3/2 kBT. So that means that there are really 3 1/2 terms. So in other words, KRMS gives you values. This is for Vx, Vy, Vz. Once again, that comes from going from a 1D gas to a 3D gas. That's where that 3 value. And what you're seeing here is that temperature does not depend on pressure, volume, and the type of gas.